Sorry for the delay. Thanks everybody for coming. This is Kuniaki Inoue. Inoue. Anyways, I've known Kuni for quite a while, so it's really fun to have him come here and give a talk here. We initially met at GFDL when we were both postdocs and doing work there through Princeton and GFDL, working with the models there. And after that, he went to NASA Goddard, and he's been for the last several years connected to NASA GISS and the Climate School at Columbia, and in particular at this Center for Climate Systems Research. I feel like there's a lot of different acronyms there that are all connected and different at the same time.
Yeah.
So maybe Kuni can explain more of that at lunchtime. He did his PhD at the University of Wisconsin, Madison, in 2016 with Larissa Back, and he also, before that, did his bachelor's degree there in forestry. So another interesting connection there is, or question was, how you got from forestry to gross moist stability.
Yeah.
I don't think he'll be telling us about that today in the talk.
A little bit, yeah.
So anyways, Kuni's work has done a lot in the last number of years to look at how the energetics of tropical convection, how that connects to the moisture and the other energetic components of the budget in the tropics, and kind of thinking about large scales and small scales and different time scales as well. I think we'll find his talk very interesting today. And we are also going to have lunch after this in the Swanson room, and then there will be time for the graduate students to meet with Kuni after that. So with that.
Thanks. Okay, thanks Levi for the good introductions, and then thanks for having me here. My name is Kuniaki Inoue, the research scientist at Columbia University and NASA Goddard. And today I'm gonna talk about the convectively coupled equatorial waves and the Madden-Julian oscillations. I just wanna talk about their structure and then also their instability mechanisms. That's what I'm kind of specialized about. All right, so let's get it started. Okay, first of all, I just want to start from this movie. And then actually it took me like 5 or 6 days to create this movie because it's an extremely high resolution movie. But you can see that this is a movie of the high resolution infrared image observed from the geostationary satellite. And then in this movie, I just want to show you how the clouds are organized in the waves. And now you can see that over the Indian Oceans, it's very active right now. Right. Okay, starting over the Indian Oceans, and then convection is now really active. And then you wanna wait a little bit. And now, yes, like huge cluster of the gigantic envelope of the cloud clusters are being developed over the Indian Oceans. And then that cluster is slowly moving to the east. Okay. Yes, now the center is around here. And yep, the center is now over the maritime continents. And eventually it dissipates. And this oscillation is called the Madden-Julian oscillations. And then this movie showing that a lot of significant fraction of the clouds in the tropics are organized by this kind of tropical wave phenomena. So today I want to talk about this wave phenomena. Again, one of the examples of the wave is this Madden-Julian oscillation called the MJO, which this shows the infrared image again. And then we have the gigantic envelope of the clouds, which is spanning entire Indian Oceans. And then this is usually initiated over the Indian Oceans and then slowly propagating to the east. And this shows the composite image of the precipitations, okay? The green is the positive anomaly of the precipitation, which is slowly propagating to the east. And then this is gonna take about 50 to 100 days to finish one cycle. And this is MJO. And MJO is one of the most important tropical phenomena because it influences a lot of extreme weather and climate events. And then this is one example. Okay, this shows the composite image of the MJO. Okay, this is the color contour represents the 200 hectopascal velocity potential or divergence field, and then overlaid with the red circle. This represents the positions. Yeah, this figure is showing the composite of the MJO with the location of the tropical cyclone genesis. So and then this green color means the positive phase of the MJO. As the MJO moves to the east, okay, the location of the tropical cyclone genesis is also propagating to the east. And then actually the location is within the envelope of the positive phase of the MJO. This is another example by the Eric Maloney and Dennis Hartman. They looked at the TC activity during the different phase of the MJO. Okay, in the westerly phase of the MJO, which is actually correspond to the positive phase of the MJO, we have more tropical cyclone activities. Therefore, like the seasonal prediction of the tropical cyclones, we need to simulate this MJO accurately. Okay, and then MJO influence other extreme weather and climate events, including the monsoon, okay, the timing of the monsoons and the total rainfall during the monsoon. This, like the monsoon is modulated by MJO a lot. Okay, and then violent tornado outbreak in the US may be modulated by also this MJO. And then MJO is of course linked to the extreme precipitation, which leads to flooding all over the globe. And then MJO may have the potential influence on the occurrence of wildfire. Therefore, like we need to understand the MJO. And then those are well documented by the review paper by the Jidong Zhang 2013. Okay, so this is another type of the wave. Okay, MJO is not the only wave. Okay, this is another type of wave, which is called the Kelvin wave. And then this shows a composite figure of the geopotential at 850 hectopascal with the wind field. And then this shade represents the brightness temperature, which is a proxy of the cloudiness. And then Kelvin wave has a very simple structures. Okay, we have the low pressure system, which is located on the equators. And then the wind field is predominantly by the zonal wind, and there is no meridional wind components. Therefore, there is no rotational wind in the Kelvin wave. So only everything is a divergence or convergence field. And then here is the convergence of the air in the lower troposphere happens, which is co-located with the cloudiness. Yeah, and then we can easily identify the Kelvin wave by looking at this kind of Homura diagram. This is a Homura diagram of the precipitations. And then you can see that the eastward propagating signals like this. And then I just plotted the high resolution infrared image at this point, okay? So this cluster is corresponding actually to the Kelvin wave. And then according to this Homura diagram, this cluster is slowly moving to the east. So this is actually the Kelvin wave. And this Kelvin wave is one of the most dominant source of the convective variability, especially over South America and Africa. Therefore, the precipitations over those regions could be significantly influenced by the Kelvin wave. Okay, another type of wave. This shows the equatorial Rossby wave. Now we have that it's the same composite. Okay, the geopotential V and then brightness temperature. And this equatorial Rossby wave is well characterized by this kind of a twin vortex structure. And the vortex patterns can be easily identified by just looking at the infrared image here. We have this very twin vortex, which is located in a symmetric way around the equators. And this equatorial Rossby wave also actually the tropical cyclones over the Indian Oceans origin from this equatorial Rossby wave. This is another type of waves. This is called the mixed Rossby gravity wave, or sometimes we call the Yanai waves. So we have very different structure, right? This is now in this equatorial Rossby wave, we have the symmetric patterns around the equators, but we now have anti-symmetric around the equators. Okay, the cloudiness, the positive anomaly is located in the northern hemisphere and negative anomaly in the southern hemisphere. So by looking at the satellite image, we can see this kind of anti-symmetric patterns, zigzagging patterns. This is kind of like characteristic properties of this mixed Raspberry gravity wave, and we can easily identify by just looking at this kind of satellite image. And then the mixed Raspberry gravity wave also become tropical cyclones in many oceanic basins. Okay, so, and then this is a final example of the waves. This is inertial gravity waves. Now the structure look like Kelvin wave, but the main difference is that we have a lot of like meridional components of the winds, therefore, which has a lot of rotational component. And one of the study by the Mehta and Adams 2021 identify this equatorial Raspberry wave during the Go Amazon field campaign. And you can see that the cluster is here, and then this cluster is moving to the west. So this is the part of the this westward inertial gravity waves. Okay, so I showed tons of different waves, and the main point is that those different type of waves organize tropical convections within the very large envelope with the distinct structure, and those waves influence the global weather and climate patterns, including tropical cyclones and monsoons, flooding, extreme precipitation, etc. And it's scientifically very important because those waves are actually the manifestations of the interactions or coupling between convection and large-scale dynamics. So if we want to understand like the interaction between the convection and large-scale circulations, you want to understand this wave phenomena. So then how do we usually investigate those tropical waves? And we usually use the Fourier analysis. Okay, we often examine the signals of the tropical waves by using the Fourier analysis, and then we showed the signal as a function of the zonal wave number and then temporal frequency like this. Okay, this is maybe you are familiar with, and then this is what we call Wheeler-Cladis diagram, named after Matt Wheeler and George Cladis. So because this analysis is kind of basis of this study, so I just want to quickly go over how to make this figure and how to read this figure. Okay, first of all, we have two different structures. Okay, symmetric around the equators versus the anti-symmetric around the equators. So the symmetric around the equators, the equator Raspberry wave is one example. Okay, about the equators, we have twin vortices patterns. Okay, so this is symmetric around the equators, but the wave has anti-symmetric around the equators, which shows this kind of zigzagging patterns. Therefore, first of all, we want to decompose any data into the symmetric component and anti-symmetric components. Okay, mathematically speaking, it's saying that we're gonna decompose into the even functions and odd functions. And then we're gonna take the two-dimensional Fourier transformations of the whatever quantities, like the OLR or precipitations or zonal wind field. And then now you get the Fourier coefficients as a function of the zonal wave number K and temporal frequency N. And then we usually plot this S square, and which is called the power spectra. And then this shows the power spectra, raw power spectra of the OLR, of the anti-symmetric component and the symmetric component. Okay, in this figure, y-axis is a zonal wave number. If you increase the zonal wave number, that means the spatial scale becomes smaller. And in the y-axis, it shows the frequency, temporal frequency. The unit is the CPD, cycle per day. So 0.5 means 1 cycle per 2 days, and 0.1 means the 1 cycle per 10 days. So here, this line corresponds to the 50-day periodicity. This line corresponds to 6-day periodicity. Okay. And now we have the positive zonal wave number and negative zonal wave number. And the positive zonal wave number corresponds eastward propagating signal, and a westward propagating signal is represented by the negative zonal wave number. Okay. And finally, we want to remove some kind of background red noise from this figure. And there are a couple different ways to remove this background noise. But so I'm not going to explain the details, but the basic idea is that you assume kind of red noise shape, and then you just want to remove it from this figure. And then this looks like this, okay? So in this figure, we have different signals associated with different waves. Okay, the blob here, the signal corresponds to the MJL, which is the strongest, the tropical variability. And this line corresponds to Kelvin wave. And this is the equator Raspberry wave, westward inertial gravity wave, eastward inertial gravity wave, and a mixed Raspberry gravity wave. And as I showed before, okay, those different waves has distinct structure. And then more importantly, those waves are excited by different mechanisms. So we need to understand those different mechanisms. So that's today's topic. And then it's very challenging to simulate those waves accurately in the current GCM. So this is an example from the latest GIST GCM. And then we have the different version of the GIST GCM depending on the tuning parameters and then different physics, different cloud microphysics. And we have now the 4 different versions. And the one versions, okay, MJO is kind of completely missing. Kelvin wave is kind of underestimated, but still there. And then antisymmetric wave is completely missing. And this is the case in these simulations too. And then in these versions, okay, now we have some kind of enhancement of the MJO, and then but Kelvin wave is still underestimated, and antisymmetric wave is completely missing. And then in the final versions, okay, now we have some kind of like strong Kelvin wave, strong MJO, strong antisymmetric waves. However, I think we're not going to submit this to the CMIP 6 because usually in order to increase this kind of variability, we have to sacrifice the climatology. So usually like mean precipitation, mean moisture field, mean temperature field is very bad in this configurations. Therefore, usually this is kind of common trade-off. If you want to increase the MJO or Kelvin wave, you have to sacrifice the mean climatologies. And then if you put the high priority on the mean climatologies, then you have to, like sacrifice the MJO. So it's still difficult to simulate those waves. And people saying like, okay, this is a problem of the convective parameterization. So why not just using the global cloud resolving model instead of the GCM or a hydrostatic model? But things are, okay, so and then, yeah, this issue is still there, even in the CMIP 6 models. So in the current version of the GCM, it's still there. And now I want to show you the results from the one of the non-hydrostatic models. That is a NICAM model from like Tokyo University in Japan. And then the panels is observations, and then they have the 2 different tuning settings of NICAM. Okay, now MJO is there, but significantly underestimated even in the non-hydrostatic model. And the Kelvin wave is also significantly underestimated. And if you're looking at the antisymmetric waves, then it's heavily underestimated. So it's not a problem of the convective parameterizations. Of course, like convective parameterization has a lot of issue, but this issue may persist even in a global cloud resolving model. Therefore, like we want to understand why, why it's so difficult to simulate this wave phenomena, because this wave phenomena influence a lot of extreme precipitation events, right?
So this one is at a higher resolution, but cloud resolving.
Yes. Yeah, I forgot what the exact simulation, but I think that's 3 kilometers or 10 kilometers gray zones. Okay. Yeah. No convection, no parameterized convection. Yes. Yep. And so like, yes, MJO and those kind of waves are significantly important, but it's still challenging to simulate those waves even in the current GCM or non-hydrostatic model. So that implies that somehow like representations of the coupling between the convection and large scale circulation is missing. It's not good enough in those models. And that kind of raises the questions. Can we trust the future projections of high impact weather and climate events like tropical cyclones, monsoons, by using those models which don't produce those wave phenomena? So that is, I don't know. Maybe you can trust it, or we cannot trust, like, who knows? So anyway, for those reasons, we need better understanding of the mechanism. So that is today's topic. Okay, so there have been a couple papers about the theory of those waves, and then we have actually the great understanding actually right now. So in this paper, which I co-authored, Adams 2019, we kind of summarize those waves in this kind of a continuous spectra. Okay, on the one side, we have gravity waves. Okay, so that's one extreme. So inertial gravity waves or mixed Raspberry gravity wave may belong to this category, gravity waves. And on the one side, we have the moisture mode. MJO and equatorial Raspberry wave belong to this moisture mode group. And then tropical depressions or Kelvin waves are kind of situated in this continuous range or continuous spectra of these two groups. And today's topic, I just want to show you that those different waves exhibit unique omega or pressure velocity profiles. And then that pressure velocity profiles explain kind of beautifully this continuous spectra of different waves. And then those differences in the omega structure actually explain the distinct instability mechanisms of those waves. That's the two things which I want to talk about today. Okay, first of all, I just want to evaluate omega profiles. Okay, so this is the kind of basis. Okay, we can explain 85% to 95% of the total variance, spatial and temporal variance of the omega profile is only explained by the two EOF. Okay, so we can express omega is just a function, linear combinations of the EOF1 and the EOF2. The EOF1 looks like this kind of first Graves mode, and then second EOF looks like sinusoidal structure, and then we can express 90% of the omega structure by just linear combination of those two different modes. So that means omega's dimensionality is approximately 2. Okay, we don't need a lot of information to construct omega. We only need 2 linearly independent information to reconstruct the whole omega structures. So that means any 2 linearly independent quantities which is associated with the omega can explain the omega structures. So for instance, if you have the omega at 800 hectopascal and 500 hectopascal, that's enough. Like you don't need omega at 200 hectopascal because omega 200 hectopascal is highly correlated with the different omegas at different altitudes in a very systematic ways. Therefore, if you have the 2 points or 2 numbers, then you can reconstruct the whole omega structures of the 90%. So using this kind of ideas, I want to characterize the whole structure of the omega with 2 properties, the top heaviness and then tilt. This represents how the top heaviness and then tilt works. Y-axis is the altitude, the pressure, and x-axis is the normalized time from 0 to 1. And here we have the structure with no tilt. There is no tilt. It's completely vertically stacked. And left columns represents tilted omega structures. Now we have kind of gradual transitions from the shallow to the deep convections. And at the same time, we have at the top panels, top heavy profiles. The top heavy profile corresponds to the very top heavy omega at the convective center here, or the convective maxima is confined to the upper troposphere. On the other hand, the bottom heavy system is now the convective maxima is happening in the lower troposphere. So by using those 2 informations, we can reconstruct the omega profiles like this, We can say like, hey, this profile is top heavy, but no tilt, or it's a very bottom heavy, but it has a lot of tilt. And we want to represent like the wave structures using those two properties. And for doing that, again, we can represent omega as just a linear combination of the UF1 and UF2. Therefore, we define the new parameter tau. Okay, new parameter tau is just a ratio between the principal component 2 and then principal component 1. But as I said previously, we need 2 degrees of freedom. We need two-dimensionality. Therefore, we define tau as a complex number, which has a real component and an imaginary component. Therefore, we have to slightly modify the first equation, okay? The omega, which is physically valid, is actually the real component of the linear component, the linear combinations of the UF1 and UF2. And now, because the tau is a complex number, we want to call the real component of the tau the top heaviness ratio, and imaginary component the tilt ratio. And actually, that real component represents how top heavy the omega profile is, and the imaginary component of the tau of this quantity represents how much tilt we have in a convective system. So for demonstrating how it works, I just want to construct a kind of canonical example, or I just started from very simple time series of the O1, and I want to reconstruct the omega by just using the top heaviness ratio and the tilt ratio. Okay, for doing that, okay, just started from the simplest time series of the O1. This is just a sign, the cosine of 2 pi x minus t plus I sine 2 pi x minus t. And for these demonstrations, I just prescribe tau. And I just want to show you like how the different value of the tau corresponds to different structure of the omega. Okay, so for these demonstrations, I specify the tau. And then by using the definitions of the tau, we can reconstruct the O2 field, okay, principal component 2. And then by using this EOF structure, we can reconstruct the omega structure by using these equations. And this is the one example, okay? The top panel, I just prescribed the top heaviness ratio, the real component of the tau, 0.3, and then tilt ratio, imaginary component, 0.2. So now we have kind of tilted and top heavy profile. And if I decrease top heaviness ratio, but keeping the tilt ratio the same, 0.2, now we have this kind of structures. Now we have the same amount of tilt, but the convective center is located in the lower troposphere. So at the convective maxima, we have the very bottom heavy profile. And then this idea works for the tilt ratio. If I reduce the tilt ratio to 0, now it's completely vertically stacked because the tilt ratio is 0. And now in these panels, we have, because of the top heavy profile, we have very top heavy profile. Sorry, we have the top heaviness ratio high. Therefore, it's very top heavy, and this is bottom heavy. And then similarly, it works for the tilt ratio. If you increase the tilt ratio, then now you have a lot of tilt. Okay, so this kind of illustration is saying that if we know those two quantities, top heaviness ratio and the tilt ratios, we can reconstruct the omega fields like this. So yes, this is given the top heaviness ratio and the tilt ratios, and also the EOF, we can reconstruct the omega profiles. And more importantly, we can quantify the amount of the top heaviness ratio and then tilt. So we want to say like, hey, this wave has more tilt or more top heaviness compared to the other waves, so that we can compare in a very objective way the structure of different waves. And this is how I compute this top heaviness ratio and then tilt ratios for different waves. And the idea is pretty simple. Okay, now we have the definitions of the tau. And by taking the two-dimensional Fourier transformations, now we can convert the equation like this. Okay, so the capital O is now the function of the zonal wave number and the temporal frequency, which is the Fourier transformation of the principal component 2. And then capital O1 is a Fourier transformation of the principal component 1. And for getting the tau, we just want to compute like this. Okay, this is a cross power between the PC1 and PC2 divided by the power spectrum of the principal component 1. And this represents actually the structure of the omega profile. And again, the real component represents the top heaviness ratio, and imaginary component represents the tilt ratio. So by doing this, we want to compute the different structure of the omega profiles for different waves. And now I just want to compute those tau, and then I just want to plot it on this in this kind of Fourier domain. And this shows the tilt ratio computed using the ERA intram for the anti-symmetric component and then symmetric components. So you can see that we have the very significant tilts over Kelvin wave, inertial gravity wave, and eastward inertial gravity wave, mixed Radsby gravity waves. Those are actually the type of the gravity waves. However, the MJO and equatorial Radsby wave, which belong to moisture mode, don't have tilt. So that is a beautiful contrast. And if you're looking at the top heaviness ratio, it's kind of opposite. Okay, this is the top heaviness ratio, again, for using the ERA intram. And now MJO and equatorial Radsby wave are very top heavy, but inertial gravity waves, mixed Radsby gravity waves, those gravity waves are kind of bottom heavy. And Kelvin wave is kind of mixture, okay, starting from the high frequency Kelvin wave. And as the Kelvin wave's frequency goes smaller and smaller, or time scale gets longer and longer, the omega profile becomes more top heavy. So we can reconstruct omega field by only using top heaviness ratio and tilt ratios for different waves like this. And just remember that we summarize the different waves as the continuous spectra like this, okay? Starting from the moisture mode, MJO and equatorial Radsby wave, which have vertically stacked and a very top heavy profile. And on the other hand, the gravity waves group, inertial gravity wave, mixed Radsby gravity wave, westward inertial gravity waves are significantly tilted and a very bottom heavy profile. And then Kelvin wave is actually the mixture between this moisture mode and gravity waves. So by using this top heaviness ratio and tilt ratios, we can represent this spectra, this continuous spectra of different type of wave. So this is the first part. Okay, the moisture mode group, the MJO and equatorial Radsby wave exhibit very top heavy, but very vertically stacked structure. On the other hand, the gravity wave mode, like inertial gravity wave, mixed Radsby gravity wave, have more bottom heavy and tilted structure. And then Kelvin wave is just a mixture between those two. So now I want to answer, how do those variations in the omega profiles relate to the different instability mechanisms? So this is what I want to talk about in the second half. And actually, like, there have been many theoretical papers, and one of the most interesting, and then I think the comprehensive one, is by this Dave Raymond 2007. And I don't want to explain all math, but those tilted structures and the top heaviness ratio are very consistent with this theoretical work. So I just want to explain this theoretical work by using just schematic instead of solving math. Okay, so first of all, what this paper is doing in their math, okay, they are looking for some kind of conditions and parameter settings which cause positive feedback. And then in their paper, they found two different modes, two different eigenmodes. Okay, one is a gravity wave mode, which is excited by positive temperature feedback. Okay, warm gets warmer and cold gets colder. And this kind of positive temperature feedback is essential for gravity wave mode. And then the other mode they found is moisture mode. Okay, this moisture mode is caused by positive moist static energy feedback. Wet get wetter and then dry get drier. And first of all, I just want to explain this gravity wave mode. And then as I showed you before, gravity wave mode have significant tilt. And then I just want to explain how that tilted structure is related to this positive temperature feedback. And actually, in the Raymond's paper, they explicitly saying that this tilt is essential, plays the most important role in the excitations of this gravity wave. So how does this positive temperature feedback work? Let me just start from the simple schematic figure. Okay, let's start from the temperature anomaly in the middle atmosphere. And if, hypothetically, if temperature anomaly excites some kind of convective variability or convections, then that's down because we have the positive anomaly and then convection is happening here. And this convection releases the latent heating, therefore, which gets the warm, get warmer kind of feedback, right? More the high temperature cause more latent heating warms up the atmosphere. So this warms up the warm area, so which has the positive feedback. And this configuration causes the positive feedback. But unfortunately, in the reality, this configuration cannot happen because usually in order to have the convections, we need some sort of buoyancy, cape. But if you have the warm temperature in the upper troposphere, that means we don't have cape. We have a lot, we have negative buoyancy. Therefore, this kind of configuration cannot trigger the convections. And in order to have vigorous convections, we have to have this kind of temperature configurations. Okay, warm air is sitting below the cold air. Therefore, we have a lot of buoyancy, a lot of cape. And then in this kind of a system, okay, convection is now initiated. And then because, if you impose this kind of temperature perturbations, atmosphere always causes the dry gravity waves, which cause this kind of temperature perturbations, right? Negative, positive, positive, negative. But this is only the dry waves. And then I'm not going to talk about the moist wave. Okay, and then in order to have positive feedback, this dry signals of the temperature needs to be coupled with these convections. And for doing that, what we want is some kind of convective inhibitions, okay? Convections must be inhibited and then confined in the lower atmosphere to make this kind of tilting structure. If there is no convective inhibitions, okay, then the convection is kind of blowing up here. And then now a lot of warming should be happening in the upper troposphere, which is kind of damping this cold temperature anomaly here, right? So temperature, the feedback doesn't happen. But if you have this kind of beautiful tilted structure, then now the positive temperature feedback is really happening because in the lower troposphere, a lot of shallow convections release the latent heating, warming up here. And then in the later stage, a lot of stratiform clouds is warming up here. So upper troposphere is warmed up. Plus, we have a lot of raindrop, which is evaporated. And then this raindrop is cooling the atmosphere. Therefore, we have the cooling effect here. Therefore, all of heating anomaly and then temperature anomalies are collocated with this kind of tilted structure. So this tilt structure is actually causing the positive feedback. And this is actually what was found in Dave Raymond's paper. And especially if you're looking at these equations, okay, so they parameterize the precipitations as a function of water vapor and then also as a function of some kind of convective inhibitions, okay? So if you have a lot of convective inhibition, which is controlled by mu sin, then they play the model a lot by changing this mu sin. And then what they found is that only when they increase musin or intensity of the convective inhibitions, they have tilted structure, and then they have instability of the gravity waves. Okay, so this is kind of consistent with their view. Okay, we need some kind of the convective inhibitions to have this kind of tilted structure, and then also the positive feedback of the temperature. So that is about the gravity wave mode. And now I want to talk about the moisture mode. Okay, this is caused by the positive moistatic energy feedback, and wet get wetter and then dry get drier. And our study indicates that top heavy omega profile is more favorable for the moisture mode instability, but there has been no theoretical paper about it, which indicates that top heavy profile is more favorable for the MJO or more favorable for the moisture mode instability. So we want to propose in my paper, we propose some sort of new hypothesis, which says that the top heavy omega profile is more favorable for the instability in the moisture mode because of its strong radiation feedback. Okay, so let me explain, because this is not a theoretical paper and then this is observational studies. Therefore, I want to explain this idea using just simple schematic figure. Okay, for the moisture mode instability, we need the positive feedback between the convection and the moist static energy. Okay, let's imagine this kind of evolution of the convective system. Okay, starting from the shallow to deep convections. And somehow, if this deeper convections has increase in the positive MSC anomalies, then which cause the positive feedback, because usually the convection prefers more moist static energy. Therefore, more convections leads to more moist static energy, and then this more moist static energy leads to more convections. So which cause the positive feedback. And actually, this mechanism is exactly same as the convective self-aggregations. And this positive feedback loop is the essential for the moisture mode instability, and then also for the convective self-aggregations. And this moisture mode instability can be decomposed into the different term of the moist static energy. Okay, H is the moist static energy, and angle brackets represents the column integrations from the surface to the top of the atmosphere. And the Eulerian tendency of the moist static energy can be decomposed into the horizontal advection term, the vertical advection, and radiation, and the surface fluxes. And then this radiation and the vertical advections are the key to this study. And then each term plays a different role in the moisture mode instability. And then let me just first explain how the radiation works. Okay, as convection develops from this shallow to deep convections, then we have the reductions of the long wave radiation at the top of the atmosphere because of this envelope clouds. Okay, therefore we have the reduction of the cooling. That means we have anomalous warming, which increase the moist static energy. Therefore, we have increase of the moist static energy, and then that increased moist static energy leads to further excitement of the convection. So radiation is usually working as a positive feedback of this kind of moisture mode feedback. Okay, radiations contributes to positive feedback, which destabilize the moisture mode. And this view is very consistent with our finding because the top heavy profiles have a lot of envelope clouds, stratiform clouds, which have very strong greenhouse effect, which have very strong positive feedback effects. Therefore, top heavy profiles with more envelope has the strong positive effects on the moisture mode. But things are a little bit complicated when considering these vertical advections. Okay, now we want to compare two different omega profiles. And let's look at, this is the canonical structure of the moist static energy. And I just want to compare how this vertical advection works in this bottom heavy system and a top heavy system. In this bottom heavy system, okay, the convergence of the air, the omega dp, is happening in this lower troposphere where the moist static energy is rich, and divergence happens in the middle troposphere where the moist static energy is poor. So in this system, moist static energy rich air is coming in, and then moist static energy poor air is exported from the system, which leads to net import of the moist static energy. So if you have this kind of circulations, you have the increase of the moist static energy within this column. On the other hand, if we have the top heavy profiles, okay, the convergence of the air happens in the altitude where the moist static energy is poor, and divergence of the air happens in the upper troposphere where the moist static energy is rich. And in this system, net export of the moist static energy. And usually this condition is called the negative gross moist stability, and this condition is called the positive gross moist stability. And this negative gross moist stability has the positive effect because it's importing positive effect on the moisture mode instability because it's importing moist static energy. And this top heavy system has a negative effect on the moisture mode instability. So we have now two competing effects, okay, radiations and vertical advections. Those are competing each other. And then this schematic shows those contrasts. Okay, in this top heavy system, we have a lot of ample and stratiform clouds which have strong greenhouse effect. Therefore, radiations contributes in a positive way to the moisture mode instability or increase the moist static energy. On the other hand, in this kind of bottom heavy system, okay, the cloud top height is very low. Therefore, greenhouse effect is very small, which have the negative effect on the moisture mode instability. On the other hand, the vertical advections exports a lot of moist static energy from this top heavy system, which has the bad effect on the moisture mode. But this bottom heavy has the good effect on the moisture mode. Therefore, if this vertical advections contributions is greater than the contributions by the radiations, that implies the bottom heavy profiles are more favorable for the moisture mode instability or MJO. And actually that was suggested by the theoretical work by Jung-Min Kwan in 2010. And in that paper, he claimed that MJL should have a bottom heavy omega profiles because bottom heavy omega profiles has a good efficiency of the moist static energy import due to the vertical advections. However, that study doesn't include any radiation effect. And if you include the radiation effect, the situation may be a little bit different. If the radiation contributions is bigger than the vertical component, the contribution by the vertical advections, then that means the top heavy profiles are more favorable for the moisture mode instability and for the MJO. And actually, this view is more consistent with our observational finding. And for verifying this idea, we actually computed the instability, okay, the intensity of each feedback by the radiation and the vertical advections in this Fourier space. Okay, this figure.
So you are showing horizontal advection instead of vertical.
Okay, so the vertical advections, I just can show you later, but can I use the blackboard?
Yep.
Yeah. So omega VHDP, this is the vertical advection, right? This is mathematically equivalent to the divergence times H. Therefore, yes, like when I talk about this kind of horizontal divergence at some altitude, which has specific moist static energy value, then I'm talking about this. And this is exactly equal to the vertical advections. So yeah, horizontal divergence is actually causing the vertical advections. So yes, yes, I'm talking about horizontal divergence, but that is the vertical advections.
10 minutes at most. Okay.
start.
Oh, okay. Sure. Yeah. Sure. Yeah. Okay.
People have to go.
Okay. So yeah, this is the stability actually of the vertical component, and this is called the gross moist stability. And this is the stability due to the vertical convections called the gross moist stability. And the reddish color means the negative feedback. Okay. On the other hand, the radiation feedback is represented computed like this. Okay. This is called the cloud radiation feedback. Again, in a Fourier space, we compute it. And sorry, the color scale is completely confusing. Now, for the radiation part, the red represents the positive instability. Okay. For the gross moist stability, red is negative. And for the cloud radiations, the positive is, the red corresponds to positive feedback. So if you subtract this minus this, you can compute the net feedback effect. This is called the effective gross moist stability. And in this figure, blue corresponds to the positive instability. So you can see that MJO and equatorial Raspberry wave tropical depressions are blue, saying that moisture mode instabilities are really happening. And that is because of this strong cloud radiation feedback. So the positive feedback, positive effects due to the radiation exceeds the negative effects due to the vertical advections in the moisture mode. Therefore, this is our new hypothesis. The top-heavy omega profiles promotes instability of the moisture mode due to its strong radiation feedback, which exceeds the damping effect of the vertical advections. Okay, so this is summary slides. Okay, we found that moisture mode group exhibit top-heavy but vertically stacked omega profiles, and the gravity waves mode have tilted structure, which is corresponding to positive temperature feedback, but which has the bottom-heavy profile. And this tilted structure is crucial for the instability due to the positive temperature feedback in the gravity wave mode. And top-heavy omega profiles are crucial for the instability in the moisture mode due to the strong radiation feedback. Okay, that's it. Thanks so much.
And this could be because there are parts maybe I couldn't follow very much. In the tilted case, when you were trying to explain the tilted, what is providing the, because it's going from.
Yep. So the instability is caused by these collocations between the latent heating source and a temperature anomaly. Right, so if you have temperature anomaly here, positive temperature here, and then we have a lot of clouds here, the latent heat is warming up, right? Therefore, which causes positive feedback. Warm temperature gets warmer. So if you keep this kind of structure, then you have the infinite growth of the system, right? Warm system gets warmer, and which causes more convections. Warm gets warmer. That is the source of the instability. What I think
It's continually kind of creating a favorable environment for more convection,
Ye-
more clouds that are going to be promoting
right,
cloud growth. Sort of the convection of moisture into that area.
right. Does it answer? Maybe we should chat about that. Yeah.
Yeah, I also have a question about this picture. So why would the anvil, let's say, goes that way? Because the tropics you expect the vertical way to be mostly east. So this kind of tilts is common in the latitudes where you explore line.
Right.
Yeah.
Right. Yes. So why in this tilted in this way? Kelvin wave, upper troposphere. Yeah, the recent study is showing that background wind is actually creating this kind of ample clouds patterns. And these directions, actually, like if you're looking at the composites, this is kind of exaggerated figures. And then if you do the composite, like we have like this kind of angle here too. And then this is angle here. And my answer is that if you have, like from the linear mode instability perspective, only this way of the stratiform clouds causing the positive feedback, therefore, which cause more instability, which makes the system bigger and then stronger. So yes, we have this directional angle clouds, but this is kind of damped faster. And then only this directional, the angle clouds can grow farther due to some instability. But that is very linear instability perspective. But if I want to look at more carefully observational data, then we might have like different or more kind of dynamical reason.
Yes, so in the moisture instability case,
Mhm.
can I say that if the radiative heating of the color
Mhm.
outcompetes the transport, then develop instability?
Mhm.
Now, so what about the propagation? The theory does not really say anything about like the eastward propagation.
Right. So the propagation is like the main theory is saying, like a lot of theory is saying that this horizontal advections is a primary driver of the propagations in such a way that MJO has kind of a gyro in the tail of the MJO, which imports the dry air into the tail, and then Kelvin wave is kind of exporting this way, and then moistened ahead of the system, so which kind of which makes the propagation to the east. So yeah, the propagation is just explained by the horizontal advections.
So basically, it's a moist the Kelvin wave.
Mhm.
The structure then is a Kelvin wave, but the speed because of the radiative impact, the speed is typically slower than Kelvin.
That is one view, and a recent study showing that MJO is actually the eastward propagating Raspberry wave because of that kind of horizontal advection of the moisture.
Showed that the radiative feedback was quite important as sort of a counterfactor.
Mhm.
How do you calculate the cloud feedback? Or what does that really mean? And just did you have any insight into what what's happening with the cloud feedback?
So yeah, this was computed just
Right there.
yeah, it's a ratio between the column integrated radiations to the precipitation.
Ratio of the column integrated
Radiation
Radiation.
divided by the
so
precipitations
like the radiative heating, the
Ra-
net radiative heating.
per unit intensity of the convections. And then in this kind of Fourier domain.
Okay.
And so that means like
So I guess it would take some work to try to figure out what maybe the different ways you could think about the cloud impact.
yeah,
I
right.
think the clouds are influencing all of that.
Mm.
So
Right.
I guess there's probably a lot of different ways the clouds could be accomplished.
Sure. So yeah, this reddish color means that the radiative warming per unit intensity of the convections is greater. So per 1 millimeter of precipitations.
Well, we're a little bit over.
Sorry.
Because it's not your fault. It's because of the technical problems that I ran into. So we're gonna stop now, but if anybody wants to ask more questions at lunch, that'd be great. Kuni be around for talking to you later this afternoon or tomorrow morning if you want. Send me an email. And otherwise, thank you very much for coming.
Thanks.